We discuss in this video how to build a customized kernel for your dataset and for your application. And the main thing here is to understand what is a valid kernel. Now, this is the so-called Mercer's theorem. And this says that a symmetric function k of x and y can be expressed as an inner product k of xy equals to phi of x, phi of y for some mapping phi if and only if k is positive semi-definite. And so what this really means is that this matrix, so that means that the matrix with its entries given by k of xi, xj, so this matrix is positive semi-definite for any collection or any data set x1 all the way to xn. So this Mercer's theorem gives us criterion for how to define a kernel function. So it's got to be so that first of all it's symmetric, and second, it's so that all of these, this matrix is positive and semi-definite. So as long as we have this, then we know that this is going to be a function that can be used as a kernel because it has this property that it's in the form of an inner product between phi of x and phi of y. And I just want to show you, if you already have a number of kernels, such as the popular kernels that we have discussed in the previous video, just want to show you, based on the Mercer's theorem, how to build on top of those extra kernels. So here is how this goes. On one hand, you can combine kernels. So I'm just writing here, you can do combination of kernels. And so what this means is that if you already have, say, two kernels, k1 of xy and k2 of xy, so somehow you already know, maybe by applying Mercer's theorem, or you are using one of the kernels for which there is a literature proof that it's a valid kernel. But if you have these, then you can also obtain a new kernel by defining it in one of the following ways. You can have a constant times one of the kernels. This is going to give you a valid kernel, or you can do the sum of the two kernels. That's also going to give us a valid kernel. And also you can do the product between the two kernels, and that's also going to give us. So all of these, so this is going to be, is a valid kernel. Or I should say all of these three are valid kernels. And this can be, of course, generalized, obviously, just by using this multiplication and introducing it here into the sum. This can be generalized to get so-called multiple kernel learning, which means that you have a number of kernels in front of you. Let's say you have K1 of X and Y, and you really have a number of these. Maybe you have M such kernels. And in fact, you can use all of them simultaneously in the following way. You just define a new kernel, K of xy. It's going to be just a weighted sum of these ones. So it's going to be sum from 1 to m of some sort of coefficient here applied to each one of these kernels. And then you are using this, and in your cross-validation method, you are going to figure out what are these coefficients that give you the best result. So in other words, you don't have to choose any one of these kernels, but you can use all of them simultaneously and leave it for the learning part to figure out which is the best balance between these kernels for your dataset. We can also do a technique that's called extending kernels. And the idea here is that you have in fact your data points, and I'm going to write them in such a way. There are some features that I'm collecting in this set A, and there are some other features of your data points that I'm collecting here in this set B. And the point here is that I have in front of me two kernels. One of them only acts on these features. It doesn't really pay attention to any one of these. So this is a kernel that applies only to these A features of X and Y. And you also have a kernel that only pays attention to the B features of your data points. So if you had such a thing, then you can extend them, and you can get a new kernel to be a sum of these kernels, Ka plus Kb. And of course this is true because taking a sum of two kernels corresponds to doing a dot product in a concatenated feature vectors.